In Jamie's flipped classroom for CS262, we're going to talk about first-order predicate logic, or fopl, as I like to call it. I don't know if that's a standard thing that people call it. First-order predicate logic is something people call it. I'm not sure about fopl. So here's the learning goals outline. I'm going to move right along and start with atoms and variables. So an atom in first-order logic or first-order predicate logic, this is a specific object drawn from a set of things. And these are typically written with a lowercase letter. So Alice is an atom, Bob is an atom, rock number 17 is an atom, and so on. All of these things are atoms. A variable, this is a placeholder. It's like a variable in a programming language or an algebra. This is a name. It starts with an uppercase letter, and it can take on any value of any atom in a particular set. And by convention, these are written starting with an uppercase letter. So, for example, X, Y, person, French pastry chef, whatever. These are variables that are placeholders that you can plug an atom from a set into. And the syntax for atoms, variables, and predicates, which we'll see in a second, these are conventions. Most of first-order logic is done by mathematicians, so the syntax is not strict in the way that it would be for a programming language. You'll see different conventions used by mathematicians versus what's used by logicians. You might see different conventions based on the textbook. There is one programming language called Prolog, which stands for Programming Logic, that basically does first-order logic. And so the syntax that I'm going to use is mostly based on Prolog because we'll do some work with Prolog later this term. But you remember, you may see different syntax, different conventions used in different places. Don't be alarmed. So let's talk about predicates, which are also sort of like relations or functions. So a predicate, these are written in lowercase, but they also have parentheses and will take some number of arguments. So for example, loves Alice Bob, you can see that down here. This means that Alice loves Bob. You can also see hates X Chris. This means X hates Chris. And of course you can see here, since X is a uppercase letter, that means that X is a variable. So this is a predicate, which basically means everybody hates Chris, which I guess was I don't know, semi-autobiographical show like maybe 10 years ago about Chris Rock, or had something to do with Chris Rock. Anyway, now what the actual predicates mean, to some extent we don't really care. We just care that it's a predicate. It's kind of like a function, and then it takes some number of arguments. And what Prolog, the programming language, is actually going to do is it's just going to take all the variables and it's going to try substituting in just all of the different atoms that it knows about and see if these predicates are true for all the possible atoms, or for some possible atoms, or for no possible atoms. So let's talk about quantifiers. This is one of the key differences between propositional logic and first-order logic. So the quantifiers, these are for all and there exists, and they're typically written an upside-down A and a backwards E. So the symbols actually look like this. You can see the upside-down A, the backwards E. It's actually hard to get these characters into Google presentations, so I'm instead going to use these like pseudo functions. You know, I can get these in, but the last time I tried doing it, I had to actually like open a separate Google Doc and then like get the symbol and then paste it in, which was kind of a pain. There might be some magic keystroke for it, but all the stuff is written using the actual sort of pseudo functions for all and there exists. So so here we've got for all x, p of x. This means that x is a variable, and it's going to range over a domain that's a set of objects. So suppose that our set contains n objects, O1 through On. For all x, p of x, this is the same as saying P is true for O1, and it's true for O2, and it's actually true for everything all the way up through On. So for all x, p of x means that P is true for everything that's in that set. Similarly, there exists x such that p of x. What does this mean? Well, essentially what you might imagine. Suppose we have that same set. There exists x such that p of x. This is equivalent to saying that P is true for either O1 or O2 or all the way up through ON. It's true for at least one of them. It might be true for all of them, but this is a weaker quantifier. It's just saying, well, there exists at least one x such that P of x, meaning one of these things must be true. I should mention there's actually an error on this slide. This should be the double arrows. It should be the biconditional. It shouldn't just be that this implies that. It should also be that the right side implies the left side, as you can see here. Operators of propositional logic, the operators that we learned, implication, biconditional, things like that, these still apply. So if we say for all x, P of x implies Q of x, it's basically the same as propositional logic. That means it's equivalent to saying for all x, not P of x or Q of x. You can kind of think of for all x, P of x implies Q of x as sort of like the equivalent of P implies Q. So all of the regular rules you can do with material implication, you can go ahead and apply in first order logic as well. So let's talk about logical arguments. These basically work the same. So to show an argument is true, you must show that all interpretations that make the premises true also make the conclusion true. And to show an argument is false, you have to find at least one interpretation that makes the premises true and the conclusion false. So that actually works the same way as in propositional logic. So a typical first order logic argument will look like something like this. So in English, would have all philosophers use logic. Socrates is a philosopher, therefore Socrates uses logic. So you would translate this into first order predicate logic, something like this. For all x, philosopher of x implies uses logic of x. So all philosophers use logic. Philosopher Socrates. Now, of course, you can see Socrates here not capitalized. That means it is, in fact, an atom. So it's one of the elements from this set of things. And so we're trying to conclude from that Socrates, therefore, must use logic. And so just kind of a visual idea of this. If this is our set, philosophers are this subset. So, these are all the philosophers. And then the whole entire sort of bean-shaped thing here, the whole set of these are the logic users. So you can see there's people up here that use logic, like Sherlock Holmes and Isaac Newton and Alan Turing. They're not philosophers, but all the philosophers in here use logic because all philosophers use logic. And since Socrates is a philosopher, we conclude, therefore, he also uses logic. Now, if there were like some little thing up here which somebody was a philosopher but like somehow was not part of the bean here, this full bean of everybody that uses logic, that would be the one interpretation, one element of this set of somebody that's a philosopher that doesn't use logic. That would show that argument is false if we could show that. But for the way it's written, we can't actually show that. This is what it looks like. So let's talk about translating quantified English sentences to first-order logic and some stuff about combining these quantifiers together. So we want to translate this sentence to first-order logic. There is someone for everyone to love. And actually, if you sort of pause this video and go to Moodle and start doing your homework, your reading check quiz, you'll see that this is one of the questions and that there's a few others. There's like a couple of questions that you need to answer. So go ahead and answer that before you go on. I'll wait because I'll be paused. On the other hand, you've now come back from pausing me. What did you come up with? Did you come up with this one? For all x, there exists a y such that x loves y. In other words, loves xy. I've decided that the loves predicate is going to mean that x loves y. So there is someone for everyone to love. And so for all x, there exists a y such that x loves y. There is someone for everyone to love. For every x, there's some y where x loves y. Now notice that there exists a y such that for all x loves xy. These look very similar. It's just we've changed the order of the quantifiers. But this changes the meaning. This means there exists a y such that x loves y for every possible x. That doesn't mean the same thing. And sometimes it's easier to think about this visually. for all x there exists a y such that x loves y, that's saying, well, for all possible x's, for each of them there exists a y. So there's some mapping where x loves y. We can sort of write it like this. However, there exists a y such that for all x loves xy. Well, this just says, well, there exists some y such that for every x, x loves y. This is just there's somebody that everybody loves. So you can't change the order of existential and universal quantifiers and have the sentence mean the same thing. It's going to mean something different if you change the order of those. On the other hand, if you have something like for all x, for all y, or there exists an x, there exists a y, you can actually change the order of those, and sometimes you'll see these written like for all x, comma y, or exists x, comma y. Sometimes you'll see these written in this shorthand. So De Morgan's law for first order expressions. This is your second question. Go ahead and try to figure this out. So if we know that there exists an x such that p of x, which of these is this equivalent to? You just have to kind of reason this out. So go ahead and pause me, I won't be offended, and then plug in your answer on the Moodle. Okay, cool. Have you done that? Fantastic. So did you come up with this one? If we know that there exists an x such that p of x, this is the same as saying, well, it's not the case that for all x, not p of x. In other words, it can't be that it's not the case that for all x, none of them are p of x, because we know there exists at least one x such that p of x. And then how about this one? For all x, p of x, what is this equivalent to? Go ahead and pause me and then give an answer. I'll wait. Did you come up with this one? So if we know that for every possible x, p of x is true, well, we know it's not the case that there exists some x such that it's not the case that p of x is true. In other words, all x's, p of x is true. So there can't possibly be some x where not p of x. Just like over here, going back a couple slides, if we know that there exists an x such that p of x, well, it can't possibly be the case that for every x, not p of x is true. And then from those, you can actually derive these other versions. There exists an x such that p of x, these are the two we just did. From these, you can actually derive these. So I'll leave that as an exercise for you. So let's do a little bit more translation. Here we go. All that glitters is not gold. This is an expression in English. It's an idiom, which essentially means, if you see something that looks like gold because it's glittering, you shouldn't get so excited because there's plenty of things that glitter, but they're not gold. It's just sort of a way of saying, beware of things that look really great, because when you get up close, they might not actually be that great. So once again, I'll go ahead and give you a chance to try this out and plug this answer into Moodle and then come back. You can pause me, I won't be offended. Okay, so moving on. Did you come up with this one? I would hope so. Because we're saying all that glitters is not gold. Well, what that means is there exists an x, so there's at least one x that glitters and is not gold. That's all we really needed to say here. All that glitters is not necessarily gold. We just needed to show that there's something that glitters that's not gold, and that proves that not everything that glitters is gold. Now, did you catch that this would have been too strong? So, for all x, not glitters x implies gold of x. This is actually too strong. Because for this to be true, glitters x implies gold of x has to be false, because we've got not this. Well, the only way to make this false is for glitters of x to be true and gold of x to be false. What this means is that nothing that glitters is gold. That's not what we were trying to say. We're just trying to say all that glitters is not gold, meaning there's something that glitters that isn't gold. So nothing that glitters is gold. That's too strong. That's not what we're looking for. And did you also catch that B was the correct answer, but A and C are actually logically equivalent? Did you catch that? I hope you caught that, because it's pretty awesome. Let me show you why. For all x, not glitters x implies gold of x. This is actually the equivalent to saying for all x, glitters x and not gold x. Here's why. Not glitters x implies gold of x. Well, this is essentially p implies q. And we can always convert p implies q to not p or q. So this is the same as saying not glitters or gold of x. Now if we apply De Morgan's law to this first part, we get glitters and not gold x, because remember we apply we go ahead and we're going to sort of distribute this not into things, which means it's going to flip the signs of glitters and gold, but it's also going to flip the logical symbol. So we're going to get glitters x and not gold x. Well, that's for all x, glitters x and not gold x. Well, check it out. These are logically equivalent. Isn't that awesome? So grammatical ambiguities. Human language is not always logical in a precise logical sense. So for example, bad pizza is better than nothing. Nothing is better than good pizza. Therefore, bad pizza is better than good pizza. You know what went wrong here? We're not really being very precise. When we say bad pizza is better than nothing, do we mean eating bad pizza is better than not eating? Living in a town with bad pizzas, living in a town without a pizza at all? You're sort of reasoning about the absence of something, and then nothing is better than good pizza. This one's a little bit easier to translate. There's no food exists that's better than good pizza, or maybe there's nothing in life that's better than eating good pizza. If we translate these a little bit more precisely, you know, you'll see that nothing in this case means two different things in these two different contexts. So pick one of these to do on Moodle. This is the sort of final little question here. The first one's actually fairly easy. All dogs are mammals. The other two are more interesting. There is someone that loves every person, sort of the final permutation of there's someone for everyone to love. And you can't always get what you want, or one cannot always get what one wants. Go ahead and try to translate those into first-order logic. Here's a good one. This is a famous idiom in English. You can fool all of the people some of the time, and you can fool some of the people all of the time, but you can't fool all the people all the time. This actually takes into account time, which first-order logic doesn't necessarily handle all that well. So, you know, what might you be able to come up with? Well, I mean, one way is to say that the act of fooling also requires time. So the first statement, you can fool all the people some of the time. Well, for all x, there exists some t such that x is a person, and x can be fooled at time t. So let's say that that's what this predicate means. X, t means, well, x can be fooled at time t. And statement number two, well, for all times, there exists an x such that x is a person, and we can fool x at time t. So this is saying you can fool some of the people all of the time. So this is a little bit different. For all times, there exists some person that can be fooled. Okay, that seems to work. And then finally, you can't fool all the people all the time. Well, for all x, there exists a t such that x is a person, and you can't fool x at time t. So every person has a time that they can't be fooled at. You can't fool all the people all the time. And you could argue that these don't precisely capture the sentiment of these statements, but it's a reasonable approximation. So now I wanted just a couple notes to wrap up on recursion and sort of a higher order logic teaser for some stuff that's beyond the scope of the course. So recursion, let's think about defining the notion of above recursively. So we want to define the notion of above. So if you think about a stack, like a stack of cafeteria trays, I guess we don't have cafeteria trays anymore, like a stack of records. I guess we don't have records anymore. Something that you stack up and put one on top of the other. Here's a way you could define this. So for all x and y, x is above y if x is directly on top of y, or there exists some z such that x is directly on top of z, and z is above y. So this above, how do we solve that? Well, we just keep recursively applying this rule. Now, in order for this to work, this means that there have to be a bunch of directly on top of facts in our list of logical statements that involve actual atoms. So we could know that, like, you know, tray 1 is directly on top of tray 2, and tray 2 is directly on top of tray 3, and tray 3 is directly on top of tray 4. And so we could use this to conclude that tray 1 is above tray 3, because it's directly on top of 2, and 2 is directly on top of 3. So we keep recursively applying this rule until we have essentially a string of directly on top ofs. But what's great is we're kind of encoding that with this above. This above actually just says, well, keep applying this rule until either, well, it says you either have a single directly on top of or a chain of directly on top ofs. So it's kind of a clever way to think about recursion. Higher order logic. First order logic, we have quantifiers that let variables range over objects. So there's sort of two major limits that we're going to talk about. Oh, excuse me. Higher order logic can't let things range over the predicates themselves. So we might want to say two predicates are the same if they both produce the same output given the same inputs. So this might look something like this. For all predicates f and g, f is the same as g, in other words, same f of g, if and only if, for all x, f of x equals g of x. So if we had the ability to have quantifiers that range over predicates themselves, we could do stuff like this. First order logic doesn't let us do that. We could also say, like, well, for all f, f is transitive if for all x, y, z, f of x and f of z implies f of x, y and f of y, z implies f of x, z. Higher order logic is much more expressive, but it's also undecidable. So there's no algorithm to efficiently figure things out. It looks like the text got cut off at the bottom there, but basically higher order logics, they're undecidable. This has a lot of negative properties. Are we going to do any higher order logic? No, not in this course, but you know, if you take math or philosophy courses, you might see this sort of stuff again. It's really cool. Other limitations, other than not being able to reason about predicates. What about probability? So if we have P implies Q, this means that Q follows from P 100% of the time. But what if Q is 37% likely to follow from P? So for example, you know, sunny days follow other sunny days. Well, that's, you know, probabilistically true, but it's not always true, because eventually there's going to be a cloudy day and based on the barometric pressure and whatever else. And so this idea of conditional probabilities, this is something that we're actually going to cover when we talk about conditional probabilities. That's going to be the next topic.